Hi, we're going to go over the Video 1 worksheet. You can find Video 1 worksheet in Canvas under Files. I'm going to put it here. You can take a screenshot if you'd like. That's the top part. And there's one bigger question on the bottom. If you want to take a screenshot, I hope it's in focus. Okay, so the purpose of this video is to plot sinusoidal functions. In particular, sinusoidal functions related to simple harmonic motion. The very first one we're going to plot, I'm going to make a big one up in the corner here of this first graph because I want to refer to it often. So the graph is y as a function of theta. This is equal to a times cosine of theta. So we're plotting a cosine theta. First I draw my axes. My vertical axis is going to be y. My horizontal axis is theta. Those are my two variables. The maximum and the minimum values of y are going to be a. A is my amplitude. The amplitude is the displacement from my equilibrium position. I call this axis equilibrium. And if this were describing a mass on a spring, the amplitude would be how far it's displaced, how far it comes away from equilibrium. The cosine graph looks like this. You can plot it using a calculator, or you could just plug in values of theta, but this one you should have memorized. An entire cycle that is going from the maximum down to the minimum back to the maximum is a length of 2 pi, or as we go through a phase of 2 pi. I'll often call whatever is inside the argument of the sine function, I'll call that a phase or a total phase. When we go through a total phase of 2 pi, we go through an entire cycle of this cosine graph. The cosine graph starts at +1, goes down to -1 when we get to theta equals pi, goes back up to +1. I'm going to leave this up here because we're going to use that as a reference. Let's plot our next graph now. Now I'm going to plot the graph as a function of time. Equals a cosine 2 pi over big T, which is our period, times time. This graph is going to look basically the same as that graph, except for with this graph we had theta as our horizontal axis. This graph we're going to have time as a horizontal axis. Since this argument is a different looking function than that argument, we're going to have different values of time than we have for theta. Now cosine only varies between 1 and -1. Even here, the biggest cosine could get is 1, the smallest it could get is -1. That's why when we multiply it by a, the biggest it can get is a, the smallest it can get is -a. So still in this case, cosine varies between 1 and -1, and our graph will vary between a and -a. When time equals 0, our argument, our total phase is 0, and cosine of 0 is still +1. And so our graph in this case is going to look just like that graph in shape. But let's break this up into 4 segments. The value here is going to be big T. Our axis here is time. Our axis here is y, which is displacement from equilibrium. Big T is the period. That's the amount of time it takes for my graph to start up here, go down here, and go up here again. Imagine we have a mass on a spring, and it's moving up and down. Our mass starts up here, goes down here, goes back up here. At time equals 0, it starts here, goes down here, and at time equals 1 period, it returns to the initial position. The period is how long does it take for it to go from its starting position and return back to its starting position. We can also write the time values in here. I broke it up into quarters, and it's very easy to break a sinusoidal graph up into quarters because it's where it crosses the x-axis where it's at a minimum, crosses the horizontal axis where it's at a maximum. We can also check to make sure we did this right by plugging in our values of time into this equation. Let's do that. So y at time equals 0 is equal to a cosine, and this whole argument turns into 0. That's equal to a. Let's do it. Y at time equals the period over 4 equals a cosine 2 pi over t times the time is period over 4. The time, t is a variable in this case, or little t. And so I'm plugging in different values of little t to determine what the value of y is at those locations. This equals a cosine of pi over 2. You can simplify this into pi over 2. Cosine of pi over 2 is 0. I go back to this graph and I see cosine of pi over 2 is 0. So therefore this is equal to a times 0 equals 0. Y of, let's plug in t over 2, equals a, I'm just plugging in 0 times t over 4 times t over 2, cosine 2 pi over t times t over 2 equals, we could cancel those out, a cosine of pi. Cosine of pi is negative 1. I could look at my reference graph real quick. This is equal to negative a. Okay, we have enough points to start this graph out. When time is 0, y is a. So time is 0, y is a. We figured out this point. When time is t over 4, y is 0. When time is t over 2, y is negative a. And so I just determined what the y positions are point by point, and I could connect the dots in a sinusoidal graph to determine what this graph looks like. You could do it with these two values if you'd like, but this is enough information for me to know what the rest of the graph looks like, so I don't need to do any more. Let's erase this. Let's do the next equation. The next equation is this, but we're going to add a phase constant into our argument of the cosine equation, or the cosine function. When we add a phase constant to this argument, we're basically shifting this graph so it starts at a different position. Cosine typically starts up here at the maximum, goes down, goes back up to the maximum. But when we add a phase constant, we make it so it's starting somewhere else. And the trick is trying to figure out where is it going to start. I know from doing this enough that when I add a phase constant, it's like I'm shifting this graph to the left. But when I subtract a phase constant, it's like I'm shifting this graph to the right. And the amount that you shift it is whatever this value is here, the value of the phase constant. So I'm going to extend this graph so that we have negative values. Cosine graph looks like that. This is negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. What we're doing is we're taking the value at negative pi over 2 and we're shifting that to our horizontal axis. And so this graph, if we just plot it, should look like this. Looks like a sine graph. In fact, when you take a cosine graph and you have a phase constant of minus pi over 2, it will always look like a sine graph. That is, it'll start at the origin, go up, then go down, back at the origin. We know the period. The period, again, is just our big T. Whatever value I give you is that period. We'll do an example next using a real time for that instead of a constant, instead of a variable, or not a variable, instead of a letter. This is time over 2. This is time over 4. This is 3 times, not time, but period over 4. This is our y-axis. This is our time axis. This is a, and this is minus a. Okay, so I figured out this graph just by taking my regular graph, shifting it, so I knew where it began. And then I could fill in the time values because I know what the period is since I put it in this format. The book will often have this equation, and it'll look like this. It'll say y is a function of time equals a cosine. It'll have omega t here, and then maybe minus pi over 2. Omega is our angular velocity. omega equals 2 pi over the period. The reason I prefer to put it in this format is I can directly read the period off, and that allows me to fill my horizontal axis. Now let's say you weren't very certain about how to shift this graph, but you needed to plot this equation. So let's plot this equation point by point. We know this is a y-axis, we know this is a time axis because those are our two variables. We know that this is a and this is minus a because the argument outside of the cosine equation is a, which is our amplitude. Let's plug in times so that we can figure out what the value is of y at each different time. We can plug in time equals 0. So y of t equals 0 is equal to a cosine 2 pi over the period times 0 minus pi over 2 equals a cosine of minus pi over 2. Cosine of minus pi over 2 is equal to 0, and so this is just equal to 0. Y at time equals 0 is 0. Now this isn't enough information to plot the graph yet because I'm not sure if it goes up or if it goes down. I'm ignoring that I already solved it the other way. So we need to solve for this next value. But what is this next value? Since I gave the equation to you in this format, you know what the period is. Since you know what the period is, I would draw the x-axis already and just try to fill in the points. We know the period is t. We know that good values to look at are quarters of this. So t over 4, 2t over 4, 3t over 4, and this is 4t over 4. Let's plug in this value into this equation. So y at time equals the period over 4, and let's solve for this. That's a cosine 2 pi over the period times the period over 4 minus pi over 2 equals a cosine, this is pi over 2, because those cancel out, that makes pi over 2, minus pi over 2 equals a cosine of 0. Cosine of 0 is 1, it's positive 1, so this is equal to a. What that means is at time period over 4, y is equal to a. Now I have enough information to connect the dots, because I know that a is a maximum, so my graph is going to look like that, and then it must follow by looking like that. We figured out the graph point by point, and up here we figured out the graph just by shifting our regular cosine graph by whatever phase constant was added to my equation. Okay, so let me get out of the way. You can see what the work looks like. Now we're going to do an example that has real numbers. For number 4, we have a mass spring system. The mass is 5 kilograms. The spring constant is 100 newtons per meter. The system is displaced 2 meters below equilibrium position. So if I draw a graph, I'm starting out at time equals 0, 2 meters below equilibrium. I know that 2 meters then will be my amplitude, because if I pull it down 2 meters, it'll go up 2 meters, down 2 meters, and it'll continue oscillating, as long as we don't lose energy to friction. The question is, graph the motion of the system. We're also going to write an equation for the motion of the system. So if I graph the motion, I know what it's going to look like. It starts here, and it'll be a cosine or a sine graph, sinusoidal. I know that this will be the period. I've been given values that allow me to calculate the period. We have an equation that the period is equal to 2 pi root m over k. When we have a heavy mass, the period is longer. It takes longer to complete one cycle. So bigger mass means longer period or bigger period. Bigger spring constant, when you have a strong spring that really pulls on the mass, stronger spring is going to make it go quicker. So a bigger spring constant, since it's in the denominator, makes a smaller period. We can solve for this, 2 pi root 5 over 100. I'm just going to solve this and make it look like 2 pi over 10 times root 5. Or we could just say pi over 5 times root 5. We can leave it in this format. On my equation or my quizzes, you don't need to solve for the decimal associated with this. This is in units of seconds because it's a period. So instead of t here, which is 1 period, I'm going to put the actual value associated with it, which is root 5 pi over 5. I could put a value right here if I want to, which is root 5 pi over 10, because it's going to be half of this value. I'm not even going to bother putting values there because it'll look too cumbersome. This is enough information, except for let's make sure we put seconds here. Let's label this a y graph. Let's label this a time graph. That's what this graph looks like. The next question says it's the same as this situation, but we double the mass. If we double the mass, we're going to make our period larger. That means if I were to try and draw the graph of double the mass on this graph, it would be a longer period. It wouldn't be double the period because we're going to take a square root of that mass. But it would be 1.4 times as long if I compared this point and this point. What I'm going to do, instead of trying to plot the graph of double the mass on the same axes, I'm just going to make a new axis. So in this case, we have a mass equals 10 kilograms. Spring constant is still 100 newtons per meter. We can solve for the period. I'm just copying my work over there, but plugging in the new numbers. 10 over 100 is equal to 2 pi root 10 over 10, or pi root 10 over 5 seconds. So my new graph, I'm not even going to try to make it to scale with that. I'm just going to plot it and change the scale of my x-axis. The graph will still start at my negative displacement, which we said was minus 2 meters. It goes up to positive 2 meters. This is a y-axis, this is a time axis. And my new period, the time it takes for it to complete one cycle, is pi root 10 over 5. Right here I could write pi root 10 over 10. These are in seconds. And this is a good answer for number 5. Okay, now we're going to start on number 6. I restarted the camera, so if I make a mistake, I don't have to restart the whole video. Number 6 says, you are watching sinusoidal waves at the ocean. Now, when I go to the beach, I usually don't see sinusoidal looking waves. So this is kind of a fictitious scenario, but that's what we're going to use. They're traveling to the right. What does this mean? We're going to draw now a graph that describes a function of y with respect to both position and time. Let me write out the general equation for this graph. This is equal to A, our amplitude, cosine. Some people use sine there, it doesn't matter, because we just add a different phase constant to switch between cosine and sine. 2 pi over lambda times x minus or plus 2 pi over the period times t plus whatever phase constant we have. This is our general equation to describe a sinusoidal graph in both space and time. Earlier, we had a mass on a spring. It was moving up and down. That is, it was changing with time, but we weren't changing the x position. It was only going up and down and is at one x position. It's like if you're watching waves on a beach and you're watching a buoy go up and down. That buoy is at one x position. So we would just count x as whatever the value is. we've pretended so far that our x position is 0, I guess, because that makes it the easiest. You can just get rid of that part of the argument, of the total phase. Let's see what this question asks. So our waves are traveling to the right. You notice here I put a minus and I put a plus. If they're traveling to the right, that's our direction of the waves, then we're going to use a minus. If we're traveling to the left, we're going to use a plus. And that's something that's easier just to memorize. The book does explain, and we explained in lecture, why that's the case by just figuring out point by point. But once you figure it out, try to memorize it. The height of a crest, so let me draw these waves. I'm not sure where they go with respect to x equals 0. I'm going to draw it versus space. So we're taking a picture of these waves. We're looking at them physically. The height of a crest is 10 meters above the height of a trough. So this distance is 10 meters. So our amplitude is the displacement from equilibrium. In this case, let's pretend equilibrium is right here in the center, and our amplitude is 5. Now, even if I was calling my y0 this, my amplitude would still be 5 meters, because it goes 5 meters above the middle and 5 meters below the middle. But in this case, we would just shift our entire graph upwards from some distance. In this case, we shifted up by the amplitude. But typically, when I draw the graphs, I'm going to draw it with my horizontal axis going right through the center of this wave. My amplitude is 5 meters, since it goes 5 meters above and 5 meters below the center of the wave. A buoy is moving up and down as the waves pass underneath. So I have a buoy here somewhere. Let's say the buoy is here. The waves are traveling to the right. Eventually, this trough is going to travel underneath the position of the buoy. And as it travels, as this entire wave physically moves, let me draw its new position. So we see the wave moved so that this position became this position. The whole wave is moving to the right, and this position became this position. As the wave travels underneath this, the buoy is going to fall down, and the position of the buoy will be right here. The time between the buoy being at a maximum and being at a minimum is 6 seconds. So what information does this give us? Well, it takes 6 seconds for my wave to travel this distance. So if I know how far this is, I could figure out how quickly the wave is moving. Also, if it takes 6 seconds to go through half a cycle, after another 6 seconds, this guy is going to go over here and it'll be at a maximum again. So this information gives us our period, the period of the buoy moving up and down. The period will be 12 seconds. Remember, the period is how long does it take for the buoy to go from its maximum position through an entire cycle back to the maximum. Well, we know it takes 6 seconds to go through half of that cycle, take another 6 seconds to go through the entire cycle, so the total period is 12 seconds. A surfer on one of the waves is using GPS. So a surfer isn't like the buoy. The surfer is actually going along with the wave, let's say. The surfer uses GPS to measure the wave speed, and he finds out that the speed, the velocity of this wave moving in that direction is 3 meters per second. Okay, what information does that give us? Well, if we know the period and we know the wave speed, we could determine what our wavelength is. The equation that relates these is that the wave speed is equal to the wavelength over the period. In this case, 3 equals wavelength over 12. So the wavelength is equal to 36 meters. Physically or spatially, what this means is that the distance between one trough and another trough, or one peak and another peak, is 36 meters. You'll notice I always use a trough or a peak. It's also the distance between this point and this point. But I don't like to say it's distance between where it's 0 and where it's 0, because it's also 0 one more time in between here. It's just passing downwards through 0 rather than upwards through 0. And so rather than get confused about whether it's going up or down through 0, I just always am consistent in using a peak or a trough. And then I don't get as confused. Okay, so we have our two variables here that we need to plug into this equation. We plug them in as constants into this equation. The only constant we have left is our phase constant, and hopefully we'll be able to figure that out. Assuming the buoy is at location x equals 9 meters. Okay, let's see what we need to draw. And it's on top of a graph, a crest at time equals 0. Draw a graph of the wave at time equals 0. So what I want to draw is a graph of the wave versus position. I know it's versus x because this entire graph will be drawn at time equals 0. Let's move our amplitude over here too. Well, I know what the wavelength is. Let's go ahead and fill in this axis. I'm going to draw 4 tick marks. One entire cycle will correspond to this position. And I know that's 36 meters. So that means this is, what's half of 36? 18 meters. This is 9. This is 27 meters. I just divided 36 by 4 and found out those different values for those segments. I know my amplitude is 5 meters, minus 5 meters. This entire graph is time equals 0. It says my buoy is at location x equals 9 meters. Clearly I chose that location to make this easy. And it's at top of a crest at time equals 0. So my buoy is located right here at the top of a crest at time equals 0. Now I have enough information to draw this entire graph. If I know the buoy's up here, I could draw the rest of my graph looking like this. Just because there's no other way to connect a cosine graph and have it be at the top position right there. Okay, let's say you weren't sure. You had this figured out where that was, but you wanted to know what the equation is. We need to figure out what the equation is anyways. We can draw the equation first, and then draw the graph using the equation. But we did backwards, that's fine. Let's go ahead and figure out what the equation is. Our equation is this. I'm going to plug in everything that we know. Y is a function of x and t equals 5 times cosine 2 pi over 36 times x minus, because it's traveling to the right, 2 pi over 12 times t plus a phase constant. We have to determine what that is. Now x and t, I'm going to leave as x and t right now. We know this graph is drawn at t equals 0, so I'm going to end up plugging in t equals 0. But we need to keep x as a variable then. So I said we're going to keep t. No, we're going to plug in t equals 0 because we want to just draw a nice one-dimensional or two-dimensional graph, however you call it. So y of x, that's the graph we're drawing, at t equals 0, equals 5 cosine 2 pi over 36. Now I'm not simplifying this. The reason I'm not going to simplify this, I like it with a 2 pi on top, because then I can just read off the wavelength directly from the bottom. Now when I plug in 0 to this, this entire term is going to become 0. So I'm just going to zap that out right now. Plus 0 plus my phase constant. Now I give you some initial conditions. I say that the buoy is located at x equals 9, and I tell you that y at that is equal to the maximum position, is equal to 5 meters. Since I give you these initial conditions, we can use these initial conditions. I forgot to put an x right here. But we can use these initial conditions to solve for our unknown, which is a phase constant. So that's equal to 5 times cosine 2 pi over 36 times x, which is 9, plus our phase constant. If I cancel these out, I know that cosine of, we can simplify this now. So that's 1 over 18 times 9, that's pi over 2. Times, there's nothing to times it by, plus 5. That's just equal to 1. So the question is, cosine of what is equal to 1? I could go back to my reference graph. Cosine of 0 is equal to 1. So I need this value to be 0. I know that pi over 2 plus our phase constant equals 0. Therefore, our phase constant is equal to negative pi over 2. So the graph, or the equation to describe this graph, is y of x, the graph is drawn at t equals 0, is equal to 5 cosine 2 pi over 36 times t, just plus my phase constant, minus pi over 2. If we have this, we can draw this graph. Remember, this graph will just be some graph where the x-axis has, or the horizontal axis has a period of 36. That's what we have here. And we're shifting our typical cosine graph to the right. If it's a negative, we're shifting it to the right by pi over 2. And so we're taking this value, shifting it to the origin, and we have a graph that starts like this. And that's the exact graph that we drew right here. And so now we have an equation that describes this graph. The graph we drew is the y position versus x. We took a photo of our waves in our buoy at time equals 0. The next question says, now draw a graph of the y position of the buoy versus time, and include an equation for this graph. Again, this is our x-axis. Okay, we're going to draw a graph of the y position versus time. The y amplitude is still going to be the same. The maximum will be 5 meters, minimum will be negative 5 meters. And I know something. This graph is drawn at time equals 0. At time equals 0, our buoy is at a maximum. So here at time equals 0, this is what I'll call time equals 0, our buoy starts up here. I know what this graph will look like. It's going to look like this. There's no other way to draw a sinusoidal function if I know where the maximum is going to be. The question is, what are the values for this horizontal axis? Well, this value is going to be what? It's going to be the period. I just erased our period. Let me redraw this. So the velocity of the wave is 3 meters per second. The wavelength is 36 meters. 3 equals wavelength over period equals 36 over period. That means the period is 12 seconds. Okay, so back to this. I drew my graph. I just need to find out what to label the period. And I know that I can label the period as 12 seconds because that is the period of our motion. That means I could put this at 6 seconds, this is 9 seconds, and this as 3 seconds. Now, since I know these values, I can almost just plug everything in, except for I don't know the value of the phase constant. I want to be sure that the phase constant doesn't change, and I'm not certain right now. And so we're just going to plug everything in from the values that we do know using our initial conditions. Again, we'll solve for the phase constant, and that's how we'll determine the equation that describes this graph. I know there's going to be no phase constant. How do we know that the phase constant in this case should be 0? The way that we know is because it starts right up at a maximum, and a typical cosine graph starts at a maximum. And so we're not shifting that graph over one way or another. But let's solve for that mathematically. I'm going to erase this graph while we do it. This graph, I better write one more piece of information to make this complete. This is taken at position x equals, what did we say, 9 meters. That's where our buoy is located. So this entire graph is located at the position of the buoy, and we're seeing its displacement versus time. Let's draw our equation. X equals 9 meters. We're drawing this graph as a function of time. Is equal to 5 cosine 2 pi over wavelength times x is 9, so I can plug that in, minus 2 pi over the period times t is our variable. That's the thing that's varying. Plus our phase constant, which is what I want to determine. equals, and we know that this, well, we need to plug in a time for it, and then we need to have an associated y. I tell you already that at time 0, y is equal to 5. It's at the maximum. That is our starting conditions. We don't need the starting conditions. We can have any pair of conditions in there to determine it. But it's easiest to determine it if we're at a maximum or a minimum. So we'll do this, because we know what the total phase must be at a maximum or a minimum. So 5, I'm just plugging 5 in for y, is equal to 5 cosine, we determined this was pi over 2, minus 2 pi over 12 times time, which is 0, plus 5.
Dr. Marshall?
Yeah. Sorry, I was interrupted there. So what we're doing is we're creating an equation for this graph. And what I need to do is solve for this phase constant. We came to this point, we plugged in conditions where I knew both the y and the t, which are my two variables. I knew at time equals 0, y was 5, and I'm doing that to solve for the phase constant. So cosine, in this case, 1, I'm going to divide out the 5's, is equal to cosine of pi over 2 plus phase constant. That's equal to 1. So my phase constant in this case is equal to negative pi over 2. Because I know cosine of 0 is equal to 1, so in order for this to be equal to 0, phi is equal to negative pi over 2. Now I just told you the phase constant is equal to 0 for that graph. Let's figure out y right now, because we need to still write out this equation. So my total equation to describe this graph is right here, and I'm going to plug in the phase constant. I already have a constant over here, so hopefully this will cancel out with that, and therefore the total phase constant for this graph will be 0. Y as a function of time, so it is at x equals 9, it's a function of time, is equal to 5 cosine. This is pi over 2, I'm looking at this guy right here, minus 2 pi over 12t plus, and this is a minus, pi over 2. And so this does cancel out with that. Perfect, that's what I wanted. My total graph is this, 5 cosine minus, this is 2 pi over 12. I'm going to keep it in that format times time. Now, using our trigonometric identities, we know that cosine of a negative argument is equal to cosine of a positive argument. So we could just take out this negative right here and make it 5 cosine of this. And that's what this graph should look like. It's a typical cosine graph starting at the maximum because we're not shifting it. The period is 12. The amplitude is 5. Okay? Let's go on to the next question. The next question, I give you two graphs. And using these two graphs of y versus x, sorry, I didn't label the axes with the variables, but you can see that they're both meters. We got to figure out what a y versus t graph looks like. Let's keep up our general equation because that's going to be used for all of our graphs that have y, x, and t in them. Let's see if I can redraw these graphs. One looks like this. One looks like this. Sorry, they're a little shifted, but this should correspond to this. This should correspond to this. This should correspond to that. We have a duck sitting right here. And sitting right here. This is at time equals 0, time equals 1 seconds. It goes up and down 0.2 meters. And I have distances here. This is 1 meter, 2 meters, 1 meter, 2 meters. Now, without even looking at the question, I guess we should look at the question, but still, I'm going to try to figure out what information do we know about this scenario. We know that the amplitude is equal to 0.2 meters. We know the wavelength. The wavelength is physically the distance between a crest and a crest, or between this point and this point on this. The wavelength is equal to 2 meters. I don't know the period yet. I need to know how fast the waves are moving to determine the period. And I can figure that out. I know this graph is taken at time equals 0, and this is time equal to 1. This must be y versus x. Both of these. Okay, we're watching a duck on a pond. The duck moves only up and down because the ripples pass underneath her. You take 2 pictures of the duck. These are the 2 pictures that we're taking. Between the pictures, you notice the wave trough moved from the left of the duck to the right. So that must be this position here. We're watching one trough travel. This trough moved from the left of the duck to the right of the duck. So it moved from here to here. And that took 1 second for it to move that far. How far did it move? It moved 1 meter, because I have our scale. This is a distance of 1 meter. And it took 1 second for it to travel 1 meter. And so I know that my velocity is 1 meter per second. Velocity equals wavelength over period. That means the period is also 2 seconds, because the wavelength is 2. Good. I know what the period is. I can basically fill out this equation now. Draw a graph of the duck's vertical position versus time and include an equation for this graph. I can draw the vertical position versus time easily without even figuring out the equation. So let's do that right now. If it doesn't come to you easily, you could go to the equation first and then draw the graph from the equation. But we're going to do the graph first, just intuitively. I'm drawing the graph versus time. The maximum and the minimum are 0.2 meters. This is time equals 0. What time should I put out here? I'm going to split this into 4 segments. And I should put the period right here. So we'll call this 2 seconds. This is 1 second. Now, time equals 0, because this whole graph is time equals 0, the duck is at equilibrium. I know the duck is also at equilibrium at time equals 1 second. So my graph is going to look like this. It's either going to go up or down. How does it go? What is the motion of the duck as time travels between 0 seconds and 1 second? Well, this trough travels underneath the duck. And so the duck is going to go down into this trough as the trough goes underneath it. And then when the trough passes it, it's going to go back up to this position. And so the motion of the duck is going to be down and then up. And then when it's here at 1 second, this crest is going to pass underneath it, and it's going to go up over the crest and back down to equilibrium. And so this is what my graph looks like. Sometimes the hard part is realizing the duck is staying stationary, it's not moving left or right, and trying to figure out how it's moving up and down. You have to try to figure out what is going underneath it. Since this trough is going underneath it, I tell you the trough goes from the left of the duck to the right. That means it must be going down into the trough and then back up to its original position. Next, we need to draw or write an equation to describe this graph. This is enough because I have 2 seconds right there, 1 second right here, time and y. So for our equation, we say x is going to be a constant in this case. X is the position of the duck. So x is equal to 2. And this graph is a y versus t graph, time. Equals a, which is our amplitude, 0.2, times cosine, 2 pi over our wavelength, which is 2 meters, times x. X is 2, so I'm just going to plug that in. Plus or minus. It's going to be minus because the wave is moving to the right from our perspective. 2 pi over the period, which is 2 seconds, times time, that's our variable, plus phi, which is our phase constant. That's what we need to solve for. In order to solve for phi, we need a set of conditions that we know the values of both y and t. Now, the trouble with this is our duck is at equilibrium at both of these positions that we wrote. Since our duck is at equilibrium, we don't know the total phase associated with that equilibrium. I'm not sure whether it's pi over 2 or 3 pi over 2. And the reason is, even though it looks like you could say, oh, this corresponds to 3 pi over 2, that's not always the case because it depends on whether this wave is moving to the right or to the left. And I always forget which one to associate it with. So what I'm going to do instead is try to find out at what time is the duck in this trough right here. At 0 seconds, he's right here. And at 1 second, this trough moves completely past it. So what is the time associated with the duck being inside of this trough, down at the bottom? And the time is 0.5 seconds. It's directly in between this and this. It's down at the bottom of the trough. So at time equals 0.5 seconds, y is equal to negative 0.2 meters. It's down at the minimum value of the amplitude. Now that I have this pair of conditions, I could plug these in and solve for my phi, for my phase constant. So y at x equals 2 meters and time equals 0.5 seconds is equal to minus 0.2 meters. That's equal to, now I'm plugging in this right-hand side. It's 0.2 cosine. 2 over 2 is 1, so this is just 2 pi minus 2 pi over 2 times, the time is 0.5, so I'm going to just call that 1/2, plus my phase constant. But what we have is negative 0.2 over 0.2, I'm dividing this side by 0.2 and that side also, equals cosine 2 pi minus, we have pi over 2, plus our phase constant. So that means negative 1 equals cosine of 2 pi minus pi over 2 is 3 pi over 2 plus our phase constant. When is cosine equal to negative 1? When the argument is equal to pi. And so 3 pi over 2 plus phi is equal to pi. That means our phase constant is equal to minus pi over 2. This is a 3. Sorry if you can't tell. Okay, I erased this stuff so that we have some space to write this equation up here. We figured out our phase constant. Let's plug it back into this equation. Y, x equals 2, time equals 0.2 cosine 2 pi minus 2 pi over 2 times time minus pi over 2. Okay, we can subtract or add 2 pi to this argument as much as I want. What I mean is, you see I drew a line up here. When I add 2 pi to my argument, I'm going from one peak to the next peak. I'm moving by an entire cycle. And if I shift this entire graph by one cycle, by 2 pi, it looks exactly the same. It doesn't change the appearance of the graph. So we can add and subtract 2 pi from this argument as much as we want. So I'm going to do is subtract 2 pi from it, and that's why I'm going to cross that out. So y is equal to 0.2 cosine minus 2 pi over 2. That's the same as just, well, I'm going to keep it in this way because I like having the wavelength on the bottom, minus pi over 2. So it's 2 pi over 2t minus pi over 2. We have an identity where cosine of negative theta equals cosine of theta. So let's take a negative out of this argument. What we get is y equals 0.2 cosine, I'm just going to say positive 2 pi over 2t plus pi over 2, because I had to take a negative out of all the parts of that argument. Okay, so this is our equation describing this graph. What this equation says is I have some argument here related to time, and I'm shifting my regular cosine graph with that argument by an amount of pi over 2. Since I'm doing plus pi over 2, I'm shifting it to the left by pi over 2. So I'm taking whatever is here at pi over 2 in my regular cosine, shifting this to the origin, and I start out with a graph that looks like that. And that's what our graph looks like right here. The other thing you could do is plug it in point by point. Plug in 0 seconds, 0.5 seconds, 1 second. Plug these values into t and solve for y at each of these positions, and you'll get a graph that looks like that. Okay, I hope that gives you some good examples to look over.